Oxidation-reduction reactions. In an oxidation-reduction reaction, we have electrons being transferred from one substance to another. These are also called redox reaction. That word always looks like red box to me and makes me want to go watch a movie. But redox is the short version of oxidation-reduction, I think because ox-red sounded dumb. Many but all of these involve oxygen. So if we have iron reacting with oxygen to form iron oxide, that's rust. This is the rusting process. Here we have C8H18 reacting with oxygen to form new compounds. That's the combustion. That's similar to, this is octane, which is in gasoline. And here we have hydrogen reacting with oxygen to form water. These are all redox reactions involving oxygen. So combustion reactions are redox reactions. Here we have a balloon full of a mixture of hydrogen gas and oxygen gas. You give that a little tiny spark and you get this. Kaboom! And we've got water and carbon dioxide. I'm sorry, not carbon dioxide. We just get water formed from that one. Combustion reactions generally give off a lot of energy. We can also have redox without combustion, without burning. Combustion requires oxygen, but you can have oxidation reduction without it. An example of this is sodium metal reacting with chlorine gas. So here we have sodium in this cool little thing here, and we have chlorine gas. And when these react together, we end up with sodium chloride, table salt. So when we have metals reacting with nonmetals, these will be oxidation-reduction reactions. Let's look at sodium reacting with oxygen, sodium reacting with chlorine. This is a metallic element and a nonmetallic element reacting together, and they form ionic compounds. Both of these involve converting an element into an ion. So here's sodium, it has no charge. In sodium oxide, that looks really weird, doesn't it? This is why we don't write charges in ionic formulas, because it gets all messy looking. We've got two sodium ions, and we've got an oxide ion. How did they become ions? A transfer of electrons. The sodium transferred electrons to the oxygen. That's oxidation reduction. Here, sodium and chlorine, similar thing happens. The sodium transfers an electron to chlorine, and we now have ions. When an element becomes an ion, the atoms have to gain or lose electrons, and those electrons do not come from the electron ATM. You can't just go withdraw or deposit electrons. They have to come from another atom or be given to another atom. So if one atom loses an electron, there has to be somebody else to get the electron. So when an atom loses an electrons, we say it's oxidized, and an atom gaining electrons is being reduced. So here, sodium, the atom going to sodium, the ion, has lost an electron, so it's oxidized. Chlorine gains electrons and is reduced. And this is how you remember that. Oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. That's another one of many things where you've got gaining and losing electrons, oxidation and reduction, and you have to match them up correctly. And unless you have some little memory hitch there, it's really, really hard. And I still think oil rig every time I look at these things. So in those examples, we had a complete transfer of electrons. We had ions being formed. It doesn't have to be a complete transformation. It can be a partial transformation. So if we look at the reaction between hydrogen and chlorine, so here's hydrogen, two identical hydrogen atoms, and they are sharing electrons between them. It's a molecule, and it's nice and symmetrical. They're sharing equally. And here's chlorine, two chlorine atoms, and they're sharing nice and evenly. When hydrogen bonds to chlorine, the electrons that are shared between them, see, this is HCl in the gas state. This is hydrogen chloride. If it was dissolved in water, it would be hydrochloric acid, and there would be ions. But acids are molecular compounds that form ions when dissolved in water. So as in the gas state, it's a molecular compound. The hydrogen and the chlorine do not share the electrons equally. Chlorine is an electron hog and takes more of them. This is like the big brother sharing the cookie with the really little brother, you know, and you give him a little tiny piece, and the big brother takes the big piece because the little guy's too young to understand yet. So what's happened here is hydrogen has lost some electron density. Oxidation is loss of electrons or electron density. So the hydrogen is oxidized, the chlorine has gained electron density, and so that's a reduction. When we have redox reactions between nonmetals, not between metals and nonmetals, but just between two nonmetals like hydrogen and chlorine, it can be a lot trickier to recognize, is that an oxidation-reduction reaction or not? And so to help identify those things, chemists came up with something called oxidation states or oxidation numbers. This is an artificial construct that we have created to help us recognize things. So oxidation states are not ionic charges. Oxidation states are not ion charges. They are imaginary charges that we assign based on a set of rules just to help us recognize these reactions. Ion charges are real and they're measurable. Oxidation states are not measurable in that way. They're made up. They're still useful. So there's a set of rules for oxidation states, and they are in order of priority. So you start at the top and you go to the bottom. And it seems a bit overwhelming at first, but then after you do it for a little while, you realize, oh, it's not that bad, actually. So free elements have an oxidation state of 0. So sodium by itself, 0. Chlorine, 0. Monatomic ions, their oxidation state equals their charge. So sodium ion is +1, because in sodium chloride, this is an ionic compound. We've got Na plus and Cl minus. So in here, chloride would have an oxidation of -1. The sum of the oxidation states of all the atoms in a compound is 0. So here we have a compound. The oxidation states of each of the elements in there has to add up to 0. If we have a neutral molecule, it's 0. If we have a polyatomic ion, the sum of all the oxidation states equals the charge on the ion. And so you can maybe see why students sometimes get oxidation states confused with charges, because a lot of times the numbers are the same. And then in their compounds, metals always have positive oxidation states or oxidation numbers. The group 1 metals are going to have an oxidation state of +1. Group 2 is going to be +2. The oxidation state often corresponds to the ionic charge. And then this is the one that requires a little bit of remembering. What about the nonmetals? We follow this table at the right. So fluorine wants an oxidation state of -1, and he has top priority. Hydrogen wants +1. Oxygen wants -2. The group 7s, the ones other than fluorine, also want -1, but fluorine gets priority. Group 6, -2. Group 5, -3. So do you see these oxidation states match the desired charges of the ions, right? I don't know. My pointer has a mind of its own. But the order here, fluorine, hydrogen, oxygen, 7, 6, 5. It's possible to have fractional oxidation states. And then we write the sign before the number for an oxidation state, after the number for an ionic charge, just to help us see that they're not the same. Okay, so now that I've explained the rules, let's play the game. Assign an oxidation state to each atom. So we'll start off with an easy one. The element chromium. What's the oxidation state on chromium? 0. Yeah, that's not a good idea, is it? Let's not use the highlighter. 0. Elements are always 0 by themselves. How about the ion chromium 3+? It's going to be, the oxidation state will be +3, same as the ionic charge. So here we have a compound, carbon tetrachloride. We have carbon and we have chlorine. And so we have to give a number for each of them. Okay, these are both nonmetals. So in the table, we start at the top. Fluorine, hydrogen, oxygen, group 7. That's where chlorine falls. Group 7, they want to be -1. It didn't say anything in the table about carbon, right? Carbon wasn't mentioned anywhere. So then we fall back on the rule that the sum of the oxidation states in a neutral molecule has to be 0. So the oxidation states of all the 5 atoms in here have to add up to 0. Well, we've got 4 chlorines, right? They're each -1 oxidation state. So that's -4. That means the carbon has to be +4. It's a lot like ion charges, but carbon tetrachloride is not an ionic compound. There are no charges. Any questions yet? Yes? Yeah, it's a lot like finding the charge on a cation. So there's 4 chlorines, and they each have an oxidation number of -1. Okay, so that adds up to -4, and there's 1 carbon, and the oxidation numbers of everything have to add up to 0. And so to add up to 0, the carbon must be +4. It's very similar to if we were looking at an ionic compound of maybe cobalt. Cobalt 4 chloride. There's 4 chlorides, and we're trying to find the charge, the ionic charge on cobalt. So it's a very similar process, and that's why students sometimes get it confused. Similar process to finding ionic charges. Does that help? SrBr2. Is this an ionic compound? Is strontium a metal? Strontium's a metal. So in here we've got strontium and we've got bromide. If you look at those rules, you go through the rules before you get to the nonmetals. No, actually, this guy comes first, doesn't he? Monatomic anions, the oxidation state is the same as their charge. So the bromide's going to be -1. And it also says that group 2A metals are going to be +2. Do the charges add up to 0? Yeah, they do. Because there's 2 of these guys, 2 bromides, so 2 -1s and 1 + 2, those add up to 0. SO3. This is a molecular compound, right? And so if you go through those rules, you see that all the oxidation states have to add up to 0, but we haven't come across the sulfur or the oxygen yet. So then at the last on that table, you've got fluorine, hydrogen, oxygen. Oxygen gets what he wants, and then sulfur is going to get what's left. Because sulfur would like to be -2, right? It's in group 6. So the oxygen gets to be -2. And then the sulfur is going to be whatever is necessary for the charges to add up to 0. So oxygen's -2, and there's 3 of them. That's -6. So the sulfur has to be +6. Did you follow that? I know it's still early. What's the name of this ion? Nitrate. So with a polyatomic ion, now the oxidation states have to add up to equal the charge. So again, we've got 2 nonmetals. Oxygen comes first in that list. Oxygen gets to be -2. And nitrogen is lower in priority. He has to be whatever is necessary. So we've got 3 oxygens, right? So that's a -6 from the oxygens. And then we've got whatever nitrogen is going to be, and that this time has to add up to -1, not 0, because there is a charge on this. So what number do I need to stick in there? 5. Any questions? We can use the concept of oxidation states to identify redox reactions. So we said that oxidation is loss of electrons. Oxidation results in an increase in oxidation state. Okay, that makes a little more sense, right, than losing and gaining. Oxidation is an increase in oxidation state, and this one's even better. Reduction is a decrease or a reduction in the oxidation state. So if it is reduced, the oxidation state goes down, and if it's oxidized, the oxidation state goes up. So if we look at this reaction, carbon reacting with sulfur to form carbon disulfide, these are 2 elements. They both start out with oxidation states of 0. In this compound, sulfur gets his choice before carbon. So the sulfur's -2. There's 2 sulfurs. The oxidation numbers have to add up to 0, so carbon must be +4. You identify the oxidation states of each of the elements, and then you look at what changed. So carbon went from 0 to +4. Oxidation state went up. Carbon is oxidized. Sulfur went from 0 to -2. His oxidation number went down. That's a reduction. So we can see that this is a redox reaction. Even though there are no charges and it's not apparent of any electrons moving back and forth, they weren't transferred, but now they've been shifted. And so it is an oxidation reduction. Any questions? Use oxidation states to identify the element that's oxidized and the element that's reduced in the following redox reaction. So there's a bunch of different elements in there. Well, tin is easy to start with because that's an element. Elements always have oxidation numbers of 0. Are there any other elements? No, that'd be too easy. Okay, what about this guy? Here we have 3 nonmetals. So the order was fluorine, hydrogen, oxygen, 765. If you do it enough, you remember it. So the hydrogen gets what it wants. The hydrogen gets to be +1. The oxygen gets to be -2. And the nitrogen has to pick up the slack. So we've got 3 -2s. That's a -6. And we have +1. And the nitrogen has to fill in the difference so they add up to 0. What's the nitrogen? +5. And this is all too messy. What about over here? This is an ionic compound, isn't it? Tin is a metal. And so here we have a monatomic anion, oxygen. Oxygen gets to be its charge, which is -2. And what's the charge on the tin? +4. NO2, molecular compound again. Fluorine, hydrogen, oxygen, 7, 6, 5. So oxygen gets its choice. Oxygen likes -2. So that's a total of -4 from the 2 oxygens. So here the oxidation number of the nitrogen is what? +4. How about in H2O? Who gets priority, hydrogen or oxygen? Hydrogen. So hydrogen is +1. What must the oxygen be? -2. Any questions about how I did that part? Now what we want to do is we want to look for elements whose oxidation state has changed. I find it helpful to start at the beginning. Well, tin. Tin went from 0 to +4. That's different. So 0 to +4. Is that oxidation or reduction? Oxidation is going up. So that's oxidation. If there's an oxidation, there has to be a reduction. Here's hydrogen. Hydrogen is +1 here. It's +1 there. Nothing. +5, +4. I think we found a reduction, didn't we? Nitrogen went from 5 to 4. That's going down. That's a reduction. Is anything else going on? Oxygen is -2. It's -2 here. It's -2 here. It's -2 there. The oxygen didn't do anything. So we drew pictures and stuff. We didn't really answer the question. So what element is oxidized? Tin. SN is oxidized. And nitrogen is reduced. Questions? Yes? Why is the second N plus 4? Good question. So when we look at NO2, the oxidation states of those 2 elements have to add up to 0. There are 2 oxygens. In the table, oxygen takes precedence, gets to be -2. There's 2 of them, that's -4. Yeah. So the N has to be +4. Any other questions? This is probably new to most of you, this whole oxidation state business. So you have to have oxidation and reduction simultaneously. If one atom loses electrons, somebody else has to take them. Okay, I hate to have to tell you this, but so we talk about oxidation and reduction, and then we also have the reducing agent and the oxidizing agent. And this can be really confusing. The reactant that reduces an element in another reactant is called the reducing agent. The reducing agent contains the element that is oxidized. Isn't that fabulous? Okay, so let's think about Hollywood. In Hollywood, you have actors and you have their agents, right? Does the agent star in the movie? No. The agent arranges for the actor to star in the movie. The reducing agent arranges for someone else to be reduced. Does that make sense? The movie agent arranges for someone else to be in the movie. The reducing agent arranges for another element to be reduced. The reducing agent gets oxidized. Yes?
I find it easy to think that the element that's oxidized is the opposite of the reducing agent.
That's true too. It's an opposite thing. Bless you. You're allergic to reducing agents. That's the problem. Sorry. So the reducing agent is oxidized. It is opposite. The oxidizing agent is reduced. The oxidizing agent is the thing that causes something else to be oxidized. So let's practice that. Determine whether or not each reaction is a redox reaction, and for the redox reactions, identify the oxidizing agent and the reducing agent. This will be fun, won't it? Yeah. Okay, first of all, we have to identify, is it a redox reaction? Well, the best way to do that is to look at oxidation numbers. I already see a typo. There's supposed to be a plus in here. What's the oxidation number or oxidation state for lithium? 0. It's an element. How about for chlorine gas? 0. It's an element. Chlorine wants to be -1. But here we have 2 chlorines. If one is -1, the other one has to be +1, and they're just never going to agree to that. So in lithium chloride, are they both 0? No. In this ionic compound, these elements are going to have oxidation states equal to their ionic charges. So lithium is going to be +1 and chloride is going to be -1. Is this a redox reaction? Yes. Which one is the oxidizing agent? The oxidizing agent got reduced. So which one of these had an oxidation state that went down? The chlorine. The chlorine's oxidation state went down. It was reduced. Therefore, it's the oxidizing agent. So chlorine is the oxidizing agent. And lithium is the reducing agent because lithium was oxidized. Anybody okay with that? I remember just being baffled by this as a student. Okay, let's look at number 2. Oxidation number for aluminum. 0. Oxidation number for tin 2+ ion. +2. Ionic charges and oxidation numbers often end up being the same number. Al3+, what's the oxidation state? +3. And tin, Sn, 0. Is this a redox reaction? Are oxidation states changing? Yes, they are. Okay, so we've got aluminum and we've got tin 2. Which is the oxidizing agent? The oxidizing agent got reduced. Tin. And then the other one must be the reducing agent. Aluminum is oxidized. Its oxidation state goes up. Therefore, it's the reducing agent. Oh wow, this one has 2 typos in it. This is a subscript 2. Okay, what about that big old mess? What's the charge on this lead ion? 2 plus. What's the charge on the lead ion over here? 2 plus. So its oxidation number in both cases is the same. How about lithium? What's its charge here? Plus 1. And what's its charge over here? Plus 1. For these metal ions, the charge is equal to the oxidation state. The other way around, the oxidation state equals the charge. Here we have a nitrate ion, and here we have a nitrate ion. Is anything happening with that? No, because the nitrate ion has a -1 charge overall, and its formula is the same here and here, so those oxidation states aren't changing, are they? And here's chloride and chloride. Those are both -1. Nothing's happening with oxidation states. Is this a redox reaction? No. There's no redox. It's a precipitation reaction, but no redox. How about this last one? What's the oxidation state for carbon solid? 0. And for oxygen? 0. In carbon dioxide, what is the oxygen? -2, and the carbon is +4. So this is redox. So oxidizing agent, reducing agent. The oxidizing agent gets reduced. Which one is going down? Oxygen's going from 0 to -2. So it's the oxygen. And with the reducing agent is oxidized, its oxidation state goes up, so that's the carbon. Any questions? That's going to take some practice, huh? Combustion reactions. Combustion reactions, things reacting with oxygen to form one or more oxygen-containing compounds, often including water. Combustion reactions also emit heat. An example, natural gas, which is mostly methane, reacts with oxygen to form carbon dioxide and water. And here we see this is a redox reaction. We've got carbon being -4. Hydrogen is +1. And in the course of this reaction, the carbon is oxidized. That's a big change for carbon, -4 to +4. The oxygen goes from 0 to -2. The hydrogen stays the same. So write, I forgot to delete that one. Write a balanced equation for the complete combustion of liquid C2H5OH. That's ethanol. The ones I'm going to ask you to do this with are going to contain carbon, hydrogen, and oxygen only, and the products will be CO2 and water. You have to remember that oxygen is a reactant. Combustion always requires oxygen. So you get CO2 and water as products, and then the challenge is balancing the equation. Leave the oxygen for last. 2 carbons, I need 2 carbons over here. Here I've got 6 hydrogens, so I'm going to put 3 over here. So I've got 6 hydrogens. Now I can look at the oxygens. I've got 1 oxygen and 2, that's 3 over here. And I've got 2 times 2 is 4. There comes a point where you maybe stop doing it in your head. 4 and 3. So that's a total of 7. So how can I get 7 oxygens on the left side? I can't mess with this one, but I need 6 from here, and so I'll put a 3 in there. So the trick on those is remembering combustion reaction is a reaction with oxygen, and if your reactant is carbon, hydrogen, and oxygen, you get carbon dioxide and water every single time.